Welcome everyone. For our last prep video, we're going to be looking at the area, how to find the area between two curves. So we've seen how to find the area under a curve. We've seen how to find the area between a curve and the x-axis. And now we're kind of upgrading so that we're looking in between a curve and another curve. All right, so let's try out. Let's look at the main result here. So if we have a function y equals f of x and a second function y equals g of x, and we're looking in between two x values, x equals a and x equals b, we can figure out the region that sits in between these two graphs by calculating the definite integral of f of x minus g of x. And for this discussion, function f of x is going to be lying above function g of x. So we're going to say y equals f of x. We're going to call that the top function. So y equals f of x is the top function, and y equals g of x, a lot of times we'll call this the bottom function. It's a lower function. All right, so where does this come from? How can we see this formula? So let's say we have two curves, f of x and g of x, and we want to get the area that sits in between those two curves over a section of the x-axis. Well, we know if we forget about curve g for a second, if it was just curve f, the way we could find that area is just by integrating. So the area under f would just be the integral going from a to b of just function f of x. Okay. Well, let's forget for a second that we have function f, and let's look at just g of x. So here's our graph of g of x. And if we wanted to figure out the area under that one, well, we could just integrate. So the area under function g in this case would just be the definite integral going from a to b of g of x. Okay. Well, we don't want this though. So the idea is we're going to go over to our region under f, and we're going to cut that out. So if I kind of draw in, do a little better than that. So imagine that we're taking we have a piece of paper here, and we draw in function g, and then we're just going to cut that out. And we're going to remove that. And when we do that, we're left with the region that we want to we're actually interested in. So we're taking the entire region under f, and we're removing the piece of the region that's also under function g. And the way you remove with mathematics is you subtract. So we're going to take this integral, and we're going to subtract off this integral. So we get the integral under f of x minus the area under g of x. And we've seen that we have integral properties that when we have two different integrals like this and the limits of integration are the same, which they are here, we can actually combine these into one integral. So f of x minus g of x. All right, so with this in mind, let's try a little example. All right, so, and let me, there we go. We're going to find the area of the region going from x equals 1 to x equals 2 between these two functions. So our two functions here are y equals 2x squared minus 4x plus 6, and the other function is y equals negative x squared plus 2x plus 1. All right, so let's look at the graph first for our region. So we're going from x equals 1 to x equals 2, so that gives us kind of the the two edges, vertical edges of our region. And then we have one of the curves, and this is the curve, which one? It's the 2x squared minus 4x plus 6. Okay. And negative x squared, that's our parabola that opens downward. So we see that one right here. Y equals negative x squared plus 2x plus 1. All right. So we want to figure out the area in between these two curves. So the idea is we're going to figure out which is the top function. And we can do this a few different ways. So if we have the graph, well, we're just looking for whichever curve is higher up on the page. And in this case, 2x squared minus 4x plus 6 fits the bill. It's higher up along the y-axis than this other curve. So just by kind of visually looking at it, we can tell that the top function is going to be 2x squared minus 4x plus 6. And that means our bottom function is going to be the other one. So the y equals negative x squared plus 2x plus 1. All right, but let's pretend for a second that we didn't actually have the graph. How could we figure this out? And we could figure it out by using a test number. So let's try t equals 1. So we can pick, for right now, because these two curves don't intersect, we can pick any number inside our interval here going from 1 to 2. So let's keep it easy. And we're going to plug, the idea is we're going to plug this t equals 1 into both of these different functions. And whichever function gives us the larger value, that's going to be our top function. So when I take t equals 1 and plug it into this first equation, we get 2 minus 4 plus 6, which is positive 4. And if I use the same test number, t equals 1, and plug it into the other function, I get y equals negative 1 plus 2 plus 1, which is positive 2. So I can see that because this value is larger, that's actually confirming that this is the top function. So this value is larger than this value. So if you didn't have the graph, you could just use a test number to figure out which is going to be the top function. All right, so now that we know we've identified the top function, now we're ready to set up the integral. So the area is going to be the integral going from 1 to 2. So we're going from x equals 1 to x equals 2. And when we set up our integration, again, the top function, whichever function's on top is we're going to put first. And then whichever was our bottom function, we're going to fill in second. So our top function was the 2x squared one. So let's fill that in, 2x squared minus 4x plus 6. And then our bottom function was the other one, so negative x squared plus 2x plus 1. And once we have this all set up, we could just jump right to the integration, but it's usually helpful to try to simplify this. So you want to try to simplify combine like terms. So in our case here, we've got 2x squared, then we're subtracting a negative x squared. So we can actually combine those. So 2x squared, the double negative becomes positive, so we actually end up with 3x squared. Then we go on, we have minus 4x minus positive 2x. So negative 4x minus 2x is going to be negative 6x. And then finally we have 6 minus 1. So that's going to be 5. So we've simplified our function down so that now, instead of having 6 terms to get the antiderivative of, we only have 3 terms. So it's going to save a bit of work. All right, so now we want to do this definite integral. So we get our antiderivative. So go for the first term, antiderivative there. The 3 is a constant multiple. We do our power rule on our x squared. So we add 1 to the exponent, take the new exponent, flip it, put it in front. Then we've got our minus 6, get the antiderivative of x. So that is 1/2 x squared. Again, there's kind of a hidden exponent of 1 there, so we're just doing our power rule. And then finally, for that 5, we multiply by x. So we end up with 5x as the antiderivative of that last piece. And then we're going to evaluate this. So we put our vertical evaluate line at the end. We're going from x equals 1 to x equals 2. And we could jump right into the evaluation, but let's simplify our antiderivative. So the 3 times 1/3 is 1, so we get x cubed. And then in the next term, the 6 times 1/2 is 3, so we get minus 3x squared plus 5x. And we're going to evaluate this. So when we do our evaluation, the way we evaluate, get the parentheses all set up. And when we do our evaluation, top number gets plugged in first, and then the bottom number gets plugged in second. So the way we evaluate a definite integral is, you can kind of remember it, it's kind of how we also set up our area formula here. So it's the top function minus the bottom function. Then later on, when we do the evaluation, we plug the top number in, and then we subtract, and then we plug the bottom number in. So it's always like this top minus bottom here. All right, so x equals 2. Let's plug it into this entire thing. So we get 2 cubed, which is 8. Then we get minus 3 times 4, so minus 12, plus 5 times 2, which is 10. And then when we plug 1 in, we're going to get powers of 1, which are all just 1. So we get 1 minus 3 plus 5. And if we simplify, we could simplify what's in the first set of parentheses. So we get 6 there, 18 minus 12. And then we're subtracting, and we can simplify what's in the second set of parentheses. So 1 minus 3 is negative 2, and then plus 5 is 3. So we end up with 6 minus 3, which is 3. And that's our area. All right, so finding the area between two curves is the main thing is we just have to figure out which is our top function and which is our bottom function. And we can just do a definite integral by setting it up where it's the top function minus the bottom function. So where we're going, and we'll look at some more examples of this in class, but we're going to see examples where our curves maybe intersect. So we're going to have to, if we have intersection points, it's going to be that we might have to split up. Figure out the area for one region first, figure out the area for the second region, and then make some adjustments and then add the results. All right, so but we'll see that in class. So we'll see you then. Bye-bye.